Hello my friends of Hydrogeological Labs. In this time we are going to do a tutorial about a fully geospatial groundwater model. Okay, so we are going to create a model from shapefiles, and then from shapefiles we are going to simulate the model. We are going to do the spatial discretization from shapefile, and as well we are going to export the shapefile. So let's see the shapefiles that we are going to work with. Okay, so we have you're going to receive on the description of the video, you are going to receive actually this, how to create a geospatial model. This is generated by the model, so actually it's not purpose. Let us okay, and then this one as well you're not going to receive on the scripts. Okay, great. So you are going to receive this on the description of the model. Okay, so we create a new model. I strongly recommend that you place this on your documents because it's easier, and then you can follow the same steps as I do. Okay, so here for example we have the general head boundary condition. Okay, so I can on the XYZ, here on the XYZ I can open OpenStreetMap. So this is the boundary condition of general head boundary. I have here a river, this is the river. I have a riparian zone. I have a recharge zone because this is the recharge from agriculture. What else do I have? Here I have some wells because actually there are some pumping wells. Okay, so this is the spatial data, and then we are going to work with this spatial data, and then we are going to create and then we have yeah, and then the discretization will be done from this from the well. So actually discretization will follow the well shapefile, I mean the contour. So because actually where the wells are located is exactly where we want our fine discretization to be. Okay, so okay, I close this. Okay, and then I open. For this tutorial we are going to work with Jupyter Lab. You can do it with Jupyter Notebook, but in this case I will work with Jupyter Lab because it's more fancy. Okay, let's see what else. Okay, so let's start. I will use in order to run Jupyter Lab. If you are working in Windows with Anaconda, you just go to Anaconda prompt and just type Jupyter Lab. Okay, great. So let's see, lab 2. I guess that you don't need this. Okay, yeah, so we have a workspace. Okay, this is new. Okay, we are in documents, then we are going to how to create a geospatial, then we are going to scripts, and then here we are going to open a new one that is a notebook. Okay, actually you can do a notebook. Okay, great. Okay, so this is exactly an overview, yeah, because like if you want to type, you need to type it, and it will, if I type it everything, it will take maybe 3 hours to do this. Okay, so this is the required package. We have operating system, NumPy, MODFLOW, Flopy. We have a PyShape. This actually comes from PyShape. If you don't have installed on Anaconda prompt, you have to type pip install PyShape. Okay, great. So in case you don't have it, in case you don't have it, from Anaconda prompt. Okay, and this will install it. Okay, great. So let's keep working. Okay, so I already have it. Then we are going to create the MODFLOW and the application of NWT. Because why are we working with NWT? Actually, not a special reason. I think that this model can work with MODFLOW 2005, but for some reason I wanted to try the NWT, so this is my NWT. Okay, then we are going to work with the areas for discretization. Okay, the areas of discretization are these: the model limit and the well, because the well is where the fine discretization will be located, and the limit is actually where the model will be conceptualized. So we run this. Okay, and then we create the figures and we create the limit. So actually from the shape file, yeah, we create the point. We have the boundary points, so x min, y min, x max, y max. Okay, and this is from the limit and from the well array as well. So we plot this and then plot it, and then here we have, this is the boundary, and this is the wells, and this is the polygon, or well, the bounding box of the well elements. Okay, that's why we call it that this is fully geospatial. Since all our data is geospatial, we can also use the MPL leaflet, because it's a quick way to see our features but with a background map, and this background map could be the background map could be any tile maps, as Google Maps, satellite, Mapbox, Bing, and so on. So with this, you just type it, and then we can see all our elements, but with a background map. And this is much helpful, because actually we can see where, we can see where our geospatial data is, and if this data is actually coherent, or like we are working with something else. So okay, so actually we see, and this is exactly the place where we are working with. Okay, so then we are going to work with the discretization. So here we have the location of the global and the local. Okay, so this is actually this is for the global and the local. So this is for the blue, and the second one is for the orange ones. Okay, and then we are going to plot we are going to calculate which are the dimensions of the model, the dimension of the total model, and the refinement. Okay, these are the dimensions of the big rectangle, and this is of the big rectangle, and this is of the refinement areas. Okay, this this tutorial, or this study case, is actually independent of the. This is actually independent of the. I mean, the discretization is independent of the grid. So actually, if you type, for example, the outer discretization will be of cell size of 100 meters, while the inner discretization will have a cell size of 50 meters. But it will regenerate if we'll say 20 meters, 10 meters, 1 meter, 0.1 meter. Okay, so because the code is actually adapts the discretization to the model grid. Okay, so this is our discretization, and then we have some array generation that works with this, that actually insert this self reference to discretization and generate the cells. Okay, well, you need to read the scripts more carefully, and then you're going to see that it takes into consideration these coordinates and this refinement, and then from this generate the cells. Okay, so we run it. This is for the array, for the column, and this is for the row. And then, well, and then, okay, then we have, this is the space in between rows. So it's the space in between rows is the column distribution. Yeah, it's kind of confusing. This is the space in between rows. This is the column distribution. This is the row distribution. That is space in between columns. Okay, so this is our arrays, and like for every discretization, every refinement size that you have, you will have a different array of columns and rows. So, and then as well you will have a different number of columns and rows. So for that we apply this and say we have 24 rows and 39 columns. Okay, great. So, and then, well, we have already the spatial discretization, I mean the horizontal discretization. We are going to work with 3 layers. With our M top will be 0, bottom will be -10, -20, -30. This is kind of similar workflow with MODFLOW. We will have 11 stress period. We will have a first stress period where without pumping, because actually the pumps will start to work on the second stress period. Okay, and the period type will be the first one will be steady, and the second ones will be transient. Okay, great. And then we can print some things about this is the length of the stress period, 1 second, and then the second ones, each stress period is of 200 days. So actually we will simulate 2000 days of pumping, where the first one has only 1 time step and the second one has 4 time step each, and the first one is steady and all the rest are transients. Okay, so we create our discretization. Okay, so this is our disc package, and then we apply our spatial reference. Okay, we apply the spatial reference because it's actually a util of Flopy. Flopy has an util that is called spatial reference. So we create a spatial reference, and then we apply that our EPSG is 32718. So it's UTM WGS 84 zone 18 south. Okay, right. So then we apply some coordinate info, and this coordinate info is actually the upper, this is the upper, no, this is the lower right, I guess, yeah, with 0, and this is for the model grid set. So that's also apply the coordinate info of where in the, this is the system of reference, and this is where the model is located on this system of reference. So you have to do it twice, but after that we can plot our model grid. Look, this is our model grid, but this model grid is also fully geospatial, because if we plot the model grid with the river and the general head, and as well the so, and then with the general head conditions using MPL leaflet, okay, it takes a while, but here we see our river, the general head boundary conditions, the wells, the model extension, and this is the generated grid. Okay, and then if you see that the generated grid actually do not match exactly with the extension of the model limit, because like if you on the logic of the logic on the discretization of cells, we follow that the outer iteration has a cell size, and the outer part has a cell size, and the refinement part has another cell size, and this and the code will create the model grid close to the as close as possible to the model limit dimension. Okay, right. Then we apply we are going to open a XYZ raster, okay, as a pandas data file. So here we have a XYZ raster, okay, and then we are going to apply this to our model top, because and then we are going to use grid data that is also a interpolation tool from SciPy. Okay, we are going to interpolate the XYZ to the cells. Okay, right, and then we can plot our model top, because it's actually this is where it's located, and here we have, this is the model top from the raster. Okay, then we can assign surface elevations and top of elevation, because okay, at the beginning we have assigned, but these were constant values, but right now we are going to reapply them. Because why are we going to reapply them? Because actually the cell thickness and the bottom of the layers will be recreated from the layer elevation. So this, and then if you want to see a cross section, you can see a cross section where actually this is the model top that comes from the raster, and it will be so and then if you change this, actually will apply for each layer, because it's actually come from the interpolation. Okay, and then we have the bottom is this is an elevation minus 120, and the and the layer bottoms are generated from the difference in between this and this. And then we can apply also K hydraulic conductivities, and then we can see the hydraulic conductivities on the cross section of our model. Okay, this is the difference, because actually this is this value, this is this value, and this is this value. Okay, and then we can we are going to conceptualize that the first and the second will be convertible, while the third will be confined. Actually, on this simulation, all layers are kept wet. Okay. And this is the specific storage and the specific yield because we need this for our for the transient simulation. Okay, so we run this. Okay, and then we need to define the bus package that is actually related to the initial heads and the active zone. Everything is active, so actually it will be called 1, and the starting head will be the initial the starting head. The initial head will be the model surface, model top. Okay, so one of the new novelties, one of the new things of this tutorial, that we were going to use grid gen. That is actually, it will be distributed also. It will be on the folder that we provide with this tutorial is the executable. You can download it as well from the USGS. But it's an excellent tool where when we want to where we want to apply or extract, where we want to apply some hydraulic parameters based on a shapefile. Okay, so we run it. Okay, and then for example, where evapotranspiration is constant of 1200 millimeters per. Okay, but on the recharge rate, it will be, where we have recharge on the vegetated parts. Okay, this is the recharge rate, but it will apply only on the cells that are intersected in this polygon. Okay. And this is the procedure you will see. So it means it will apply on all of these cells. Okay, and okay, select the cells that are actually inside. This is a part of the list. This is a part of the list of the cells that are in this polygon, and this is the part of the code that will apply for these cells. Yeah, apply the recharge rate, and then we apply it to the recharge. Okay, so we can apply this is a representation of the recharge rate, and then we see that recharge is applied on this and this. Well, the river cells are where the river cells are not applied, because actually is not located on the recharge polygons. Okay, so we can apply the wells as well. We are going to apply the wells. The wells are points, and as well we at the beginning there is no pumping, so we create an empty rear low column rate. Okay, but for the rest we apply it based on the cells intersected on this shapefile. Yeah. Okay, and then we apply to the well package. We create the well package, and then we can see with a figure of the cells conceptualized as wells on our model. So these are the wells, and these are the cells conceptualized as wells. Okay. Then we see the river package. This is the river package, and the river is this one. Okay, and this is the same. So we have a polygon of the river, and then we are going to apply for the cells intersected in these polygons. We are going to apply the river package. So if we want to see, these are the cells conceptualized as river. Then we have as well, on a similar procedure, we have as well the general head boundary, because we have a regional flow that flows from east to west. So these are the cells. Okay, and as well the general head on the east is 90 meters and on the west is 50 meters. So this code will apply this to the cell. We apply this to the model, and then we can see the results of the shapefile and the corresponding. We can see the results of the shapefile and the corresponding cells here. Okay, then we apply the output control, because we want to see the result for all the all the time steps. Okay, so we have to specify this, and in Flopy we have to specify this for every time step. So actually I have created a loop on this, and then we create an output control object, and then after this, if we are happy, we write and run. Okay, pretty easy. No, pretty fast. It's not easy, so it's less than 1 second. So, and then we can import the results with the utilitary head file. Okay, and then we can if we are going to import just the last result, because with this data, if we don't specify the time step, is actually only the last. So this will be at the end. Okay, we are going to create a visualization of the heads, contours, cells, labels on the contour, the mesh, the conductivity, and some spatial data. So if we apply this, so this is a representation. I can see that it might be that this is 12 and this is 8. Okay, so here we have, this is actually 90, this is 84, this is 50, 50, this is 60, 64, and this is the river. We can see that in this part the river is above the water level, and also the river is applying water to the system, and here the river is pumping water out of the system. Okay, and then since all our data is geospatial, we can also provide a background map, or like online map, to our results, and this is very powerful for us. Okay, so we are going to apply the Google terrain to our results. It actually takes a little while. I don't know why, maybe because of the amount of dots. Takes a while, but the results is quite good. So you can have here the wells, the model extension, the grid, the boundary conditions, and how the water is flowing. Okay, and then we can do a cross section to see how is the development of the water section. Okay, so as you have seen, this is a simple, it's not basic, it's a simple example of a fully geospatial model. Okay, if you see on the conceptualization of the boundary conditions, if you want more like more boundary conditions, so it's just a matter that you insert more. My recommendation is that you follow this tutorial. Yeah, you see how this works. Yeah, you see how is the how and why every part is installed, is conceptualized there. Okay, and after this you can implement this for your own you can implement this for your own examples or thesis or projects and so on. Okay, so that was all my recommendation. We are from Hatari Labs. We are a blog dedicated to knowledge sharing open source software, especially in groundwater. Okay, so if you like what we do, please sign up for our YouTube channel, give it a like, share it through your friends. Soon because we have some people that have reference our tutorials in their research projects, papers and so on, so we are going to provide a research gate. So actually it's important also for us that if you use our tutorial for any research, just a reference to us, because well, it's nice to be referenced. Okay, my name is Saul Montoya from Lima, Peru. It was a pleasure to bring you this tutorial and hope to see you in comment tutorial. Have a great day. Bye bye. Bye.